Hello everyone, welcome back to Power System, class number 17. In this class, we're going to talk about power system optimization or so-called optimal dispatch of generation. What this means that um, let's say your company has a 4 or 5 different power plant, right? You're trying to deliver the load to your customers by optimizing generation, what actually minimizing the cost of generation, right? So this is the goal here. So we're trying to minimize the cost of generation while supplying the demand for the customer. And this is also called optimal power flow. And this is the basically show you how it works. If you have all kinds of different power plant here, and you're trying to minimize the cost while you're delivering the power to your customer. And to do that, you're basically working on 2 different power generation here: real power and the reactive power, right? Uh, Power generation plant can generate both power. While you're generating the power, you're basically using some kind of fuel. So this fuel will cost you money. So, and also your efficiency of the power plant also comes into play, as well as loss in the line also comes into play. So you have to put everything together in your optimization modeling to minimize the cost of generation. In this chapter, we basically make it a simple introduction to the optimization. We're considering only real power. We're not considering reactive power, as well as I don't think I can go into the loss, inclusion of loss into the optimization equation. So my goal is to give you optimization introduction by using real power as well as the real power constraint. That means your power system cannot generate ultimate unlimited power. Also, it have to have a minimum power generation to make the cost, right? So there's a limit. What is the minimum? What is the maximum? We're going to include the maximum, minimum generation of the power plant into the equations only for real power. We're not going to consider any reactive power, as well as we're not going to include the losses into the equations. So this is very active research area in power system because it saves money, right? So when you money involved into something, there are a lot of research going on. So this is a lot of research going on in the optimization. The first very simple optimization thing would be without any constraint. So like unconstrained parameter optimization. To understand that, then you can get to the constraint. And we need help from the numerical analysis. We're gonna get into that, a new branch of math. Then if you have unconstrained function, let's say this function, there's no constraint attached to this function. I'm trying to minimize, find the minimum value of this function. To do that, I have to find basically first partial derivative of that function with respect to each of the variables. This is right here, right? Then we're gonna set them equal to 0 and solve this system of equation to find the x1, 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 x2, x3, all those variables, then find the minimum value. But to be sure that we have a minimum value, we need to take a second derivative, right, and form a matrix, and that is called Hessian matrix over here. It's called Hessian matrix. That matrix, if that matrix is positive definitive matrix, then we have a minimum value. So this is the Hessian matrix over here. Hessian matrix is symmetric. That means if you go along the diagonal, this would be a mirror image. That means this would be the same value, all right? So when a matrix, a definitive positive matrix, that means it's all positive eigenvalues. You know what the eigenvalue is. You can simply use EIG and a matrix like symmetric H over here to find the eigenvalues from MATLAB. So let's work with this simple function over here. So I have the function of the 3 different variables. So I have 3 different partial derivative over here, and I set them equal to 0, right? Then I also can rearrange them like this, then make it a matrix format over here. To solve this x1, x2, x3, I can take the inverse of this one like that, then find the x1, x2, x3 value. You all know this technique. Then we come here, these are the values for x1, x2, and if I put that value into the function, I get a 2. So we're saying that 2 is your minimum value. But to be sure, I have to form a Hessian matrix, right? So let's take this thing out of here. All right. So to find the Hessian matrix over here, I brought all those three equations over here, first derivative. Then I'm going to take the second derivative of each of them. If I take the second derivative of this guy over here, sorry. If I take the second derivative of this one over here, first with respect to x1, I get 2. With respect to x2, I get 1. With respect to x3, I get 0, right? So that's right here. Then I can do the same thing for the second one. With respect to x1, I get 1. With respect to x2, I get 4. With respect to x3, I get 1. And same with the third function. So this is the Hessian matrix, right? So if I use this comment here on the MATLAB, that I get all those values of this one. As you see, all of them are positive, so there's a positive definitive matrix. That means this is the minimum value for the function, all right? So that is unconstrained. Now, what if you have constraint? So that means now we have a function. We also call it cost function. We're trying to minimize, and that is subject to a constraint right here, right? So if I have that, I have to find a new function combining these two. Is called Lagrange multiplier method. So I have a new function over here combining these two functions, f here, right? Then your constraint over here with the multiplication of Lagrange multiplier, right? So then I'm trying to find the minimum value of this function over here using the same method. So that means I'm taking the partial derivative of that one with respect to variables and also with respect to the multiplier, right? Now, to put an example together here, so this is your constraint, right? This is the subject to a circle over here, and this is the function I'm trying to optimize with the distance from the center, distance from the origin, right? So this is the function I'm trying to optimize with respect to this, which is my constraint. I have to find the minimum on this function, on this circle, right? So if I put this together with the Lagrange multiplier, I put the equation here for you again. And if I put it back together here, this is the function right here. Then this is the Lagrange multiplier lambda, then the g, right? So now I can find the three different partial derivative of this one over here, and I can also rearrange the x and y value from this equation over here, then put it back to this function over here to find the lambda. If I do that, your lambda becomes 1 and -3, right? So now also get back to the Hessian matrix over here. If I try the second derivative of this one with respect to x, I get 2 plus 2 lambda, and with respect to y, I get 0 for this function over here, right? Second derivative with respect to x is 0, with respect to y is 2 plus 2 lambda. So this is my Hessian matrix, right? So I have both of them, right? So now this is x and y when lambda equal to 1. This is x and y value when lambda equal to -3. So which one is minimum? So I can do that by examining my Hessian matrix. So this is the Hessian matrix over here. Then for xy 4, 3 point, lambda is 1. I put the lambda back here. Then this is my Hessian matrix for x, y value 4 and 3. Then my eigenvalue is 4 and 4. So both are positive. That means it's positive definitive matrix, right? If I do the same thing for lambda -3, I have the both value is negative. That means this is not a positive definitive matrix. That means the 4, 3 is my minimum. So this is your minimum here, all right? So that's how you determine who's the minimum, who's not, by using Hessian matrix. This is can be done, this kind of technique can be done for a simple problem. But if a problem is more complicated, if you add reactive power to it, you add line loss to it, you have more than 2, 3, 4 power plant there, is get complicated. So we need a method called iterative process. This iterative process, one of them is Newton-Raphson. We're gonna talk about that in the next lecture.